doing an integral in spherical coordinates will ultimately not be that much different than doing one in, say, cylindrical coordinates. We just have to understand what the replacements and conversions are. So we use our typical replacements for x, y, and z for spherical coordinates. And we should still remember these from our work with spherical coordinates before. X is equal to rho sine phi and cosine theta. Y is equal to rho sine phi sine theta. And z is equal to rho cosine phi. Particularly when we go to convert our function to spherical coordinates, we need to make those replacements. The other part of this we know is we're going to have to come up with a representation for what dv is for spherical coordinates. So I've sketched out what is a differential chunk over here for us to look at, and this is just trying to illustrate what a typical chunk would look like as we fill up our volume with these little pieces. And I don't want to deal too much with the details of why the volume comes out to be what it is. The volume that we get for dv in spherical coordinates is going to be given as rho squared sine phi d rho d phi d theta. So now we have all the pieces, we just need to make sure that we get our bounds. And once we have those bounds, we can set up and solve our integral. So something else we want to make sure we kind of pay attention to is that it's not unusual for us to define these volumes by bounding the rho by functions. So that means that these outer surfaces and this inner surface here will oftentimes be, and I'm talking about the one in behind here, that inner surface and that outer surface will oftentimes be defined as functions. So maybe these functions are, say, g1 of theta and phi, and maybe this outer function here is g2 of theta and phi. So we should just be aware that those kinds of situations can happen depending on what kind of a volume that we're working on.